Okay, great. Hello, everyone. We are very happy to have Dr. Alex Cloninger to give our 1W-MINDS seminar. He is now a professor in the Department of Mathematics and the Halishiglu Data Science Institute at the University of California, San Diego. He received his PhD in applied mathematics and scientific computation from the University of Maryland. And later, he held an NSF postdoc fellowship and served as a GIPS assistant professor of mathematics at Yale University. His research focused on geometric data analysis and applied harmonic analysis, with an emphasis on methods that model data as locally low-dimensional, such as data concentrated near manifolds or subspaces. These problems image in a wide range of scientific disciplines, including the imaging, medicine, and AI. The techniques he developed are closely connected to the modern machine learning and the statistic framework, including deep learning, network analysis, and the study of distance between probability distributions. So today, Alex will talk about the geometric as well bottom-up manifold learning. Alex, it's your turn.
Awesome. Thank you. Thank you so much to the organizers for this. As a former organizer, it's now really fun to be on the other side and actually get to give a talk. Yeah, so what I'm going to talk about today is, bottom-up manifold learning, which is kind of a research line that we've had over the last few years. And I'm going to kind of give an overview of a handful of papers from this, this perspective. So the first thing I want to mention is specifically Dhruv. So Dhruv was a student, PhD student here that was co-advised by myself and by Gal Mishne, who's a professor at HDSI and a close colleague of mine. This work is driven by Dhruv. Dhruv is an insanely amazing mathematician and data scientist. So now he is a postdoc at Princeton and will be on the job market, in a few years. And I cannot recommend Dhruv highly enough. He is an incredible researcher. Gal, she's got tenure, so I don't need to rave about how great Gal is, but also awesome colleague. And then this is also some additional collaborators, my student Sawyer, and then a couple of colleagues that have run some of the neuroscience stuff that we're working on. Okay, so what are we going to talk about today? I'm going to just generally talk about the idea of bottom-up manifold learning. So maybe a lot of you already are familiar with this idea, but a lot of data often lies near sort of lower dimensional geometric structures. The data is not space filling in high dimensions. And so what we're looking to do is recover some sort of low dimensional set of coordinates of that high dimensional data. And there are examples where you truly do get manifold structure. One is you look at these types of molecules that vibrate and rotate and transition in a bunch of different ways. It turns out they can't just completely fill the 24-dimensional space because there's chemical constraints. And so they actually wind up following some low-dimensional manifold structure. I'll talk a little bit about that. I'll also talk a little bit about neuroscience, where you're studying some neurons of a brain of a monkey or a rat. And even though you have a lot of neurons that are firing in this very high-dimensional fashion, it's really explaining a low-dimensional phenomenon, and you want to recover it from the high-dimensional data. And similarly with mouse brains running around. So I'll get to some of that in a minute. And so I think there's a lot of benefit to this kind of framework, right? There's visualization, there's modeling latent dynamics, behavioral decoding, all of this. But how do we do it? Like, that's kind of the question, right? So a lot of the techniques people probably are familiar with in manifold learning are what I'm going to call top-down manifold. So what I mean by that is you wind up creating some global structure on your data, a graph or something like that, and then you try to find a low-dimensional coordinate system. Laplacian eigenmaps falls into this, diffusion maps. UMAP, TSNE, if you're familiar with these, they have a second component, which is called a local refinement. Once you create an embedding, you kind of reshape it a little bit in order to better match your high-dimensional data. But all of these fall into this structure, which is basically lay down everything in your best coordinate system and try to refine globally. And I have a different perspective of this. And I'm not the only one to have this perspective. This exists before, but I'm going to think about what I'm going to call bottom-up manifold. So in bottom-up manifold learning, what we're going to do is we're actually going to try to create overlapping patches. And in those patches, we're going to spend a lot of time trying to ensure that the data in that patch is being represented accurately and with low deformation. And once we've done that, we'll have all of these separate views of our manifold that theoretically are completely disjoint from each other. And then once we're certain that we have that sort of nice low-dimensional local coordinate system, we're going to try to piece them together. And that's going to be called the alignment of the local views. And I'm going to go through this entire pipeline of how do you talk about local views, how do you align local views, how do you prove bounds on these local views, all of this. So again, we are not the first to do this. If you've ever seen LTSA, local tangent space alignment, this is doing something similar, Hessian eigenmaps, all of these different things. And then there's the recent work that we've been doing that I'm going to really focus in this talk. So I really want to answer like 3 central questions. The first question is, how do we construct low-dimensional, low-distortion views? And how do we make sure they're robust to noise? The second is, how do we actually align them in an efficient, robust manner and produce global bounds on distortion? And the third is, once we have low distortion embeddings, how does that help us in the downstream analysis? How can we actually use this to do real downstream like science at the end of the day? Okay, so those are kind of the 3 central questions I'm going to focus on. So I'm going to go in that order. Sorry, I do want to mention one thing. There's this very funny aspect of how I give this talk, which is that basically there's a chicken and the egg problem. I can talk about local views and then say, oh, look, they're really good at creating global embeddings, and then talk about the how to build the global embeddings. Or I can talk about the global embeddings and say, I promise you there are good local views, and then later talk about how I know there are good local views. So it turns out that like they're interconnected with each other, so I kind of just have to choose an a priori order. So I'm going to start by talking about local, then patching, then downstream application. But it's possible at certain times that I will show you a patched manifold without really explaining how we got there. And then later in the talk, I will really explain how we got there. Okay? So local view construction. First thing, how do we construct these local, low-dimensional, low distortion local views? All right. First pass guess of how you could do this is local PCA, right? You take k-nearest neighbors, you do some local covariance of these things, you do PCA to estimate the tangent space. This is actually what most local algorithms do, what most bottom-up algorithms do. And this is nice if your data truly lives on a low-dimensional surface, and if your data is densely sampled enough that that covariance estimate is statistically good, right? You have enough points that in a local neighborhood, you can have statistical certainty of your low-dimensional coordinate system, your low-dimensional PCA. But that breaks down. And in particular, it breaks down when you have noisy manifolds. So I have an example here, which is just a little kind of, high curvature manifold. And at each point on the left image over here, I'm showing you what the estimate of the local PCA, kind of the local gradients would look like. And you can get a good idea of sort of how everything is moving. By the way, I should say these are extrinsic gradients, just to be clear. But then when you go to noise, everything breaks down. Because if you think about it, if you're in a low SNR, if you're in a high SNR region, a region where you really do have some low dimensional structure, okay, then your data does look low dimensional, and you can probably get a good estimate of the principal directions. But if you're in a low SNR, high noise area, you get this image that's down here. Look at a local neighborhood. It basically looks full dimensional. So PCA is not going to give you anything correct in that region, right? So one would say that the trade-off would be you make your neighborhood bigger and estimate PCA there. But the flip side of that is that now you have model bias. Now your manifold is curving all over the place and you're trying to fit a hyperplane to it. That's probably going to have its issues as well. So we really want to think about how to reduce that noise as we're doing the dimension reduction. Okay, and that's what I'm going to focus on here. Yeah, so this is the idea. There's some, choosing a neighborhood greater than the scale of the noise, less than the curvature. There are bounds on this. There's some really good work done by Anna Little, by Marmagione, by a bunch of people in this space, right? And again, that's the problem, is that these bounds are in terms of noise level, curvature, and reach, and there's really nothing you can do about it if you're doing local PCA. So I want to talk about something else. Our idea is we're going to move back to thinking about eigenfunctions of kernels in Laplacian. I'm not going to do Laplacian eigenmaps, so don't have that in your mind. But we're going to start with the same framework. You have all of your data, you build a graph on it, you create some eigenfunctions. Specifically, we're creating a random walk Laplacian, and then we're going to take some eigenfunctions. Okay, now there's all this literature. Random walk Laplacian converges to some Fokker-Planck equation with high probability. First few eigenfunctions. When you do Laplacian eigenmaps, what do? You keep the first few eigenfunctions, and you call that the low-dimensional structure. It is very nice to do that, but the problem is that if you have a d-dimensional coordinate system, it is very, very, very rare that it is explained by the first d eigenfunctions. It does not always work that way. And if it does not work, then you're going to lead to collapse in your embedding, and that's a problem. So the first thing we did was a paper that we call LDLE. I'm not going to focus on this too much, but I just want to mention that what we did was we actually borrowed from this really cool result from Jones, Magione, and Schul that says that actually in a small neighborhood, there exists a subset of low-frequency eigenfunctions that are going to be almost orthogonal to each other. And so we used that. We would just take some eigenfunctions and pick two that were almost orthogonal to each other. And we would call that our intrinsic coordinate system for that patch. The key being intrinsic, because it's defined within the eigenfunctions, right? And this works, and you can do some really cool stuff. But I'm going to talk about an extension of this, which is now, to me, I'm going to say the gold standard of how to do this, right? So if you're familiar with the LDLE work, if you've seen Gall talk about it, it's awesome. But we've kind of moved beyond how to think about the local neighborhoods. So I really want to delve into thinking about how to create these local patches, again, using eigenfunctions. But it gets into this thing that we are calling LEGO, which is Laplacian eigenvector gradient orthogonalization. So we're really sitting in a setting here where you have some submanifold that's nice and smooth. But that's not the data you get. The data you get is specifically going to come from some tubular neighborhood around your manifold. Okay? And that is the problem for local PCA. So what we're going to do, I'm going to describe the algorithm first and then motivate it. But this relies on what I'm going to call an assumption, and then I'm going to start giving you reasons that this assumption is correct. But there is sort of folk knowledge in this manifold learning community that the low frequency eigenfunctions, the first few eigenfunctions of your Laplacian, are highly robust to noise. They vary along the submanifold and are constant in the normal direction that arcs out the tubular neighborhood. That I am currently stating as an assumption, but in a few slides, I will give you some proofs of this being the case. But assuming that is true, now if you have these eigenfunctions, okay, they are only varying along the submanifold direction. And similarly, we can try to create gradients of these eigenfunctions. Now, I'll tell you how to do this. So now that you have gradients of eigenfunctions that are only varying along the submanifold, that gives you a wonderful extrinsic coordinate system that is parallel to local PCA. It's giving you a low-dimensional projection matrix. It's telling you it really is projecting onto a subspace, like in that little neighborhood. Okay. And that's the idea. That's what this algorithm is. That's what this whole paper is going to is about, basically. So I want to describe the algorithm, and then I want to explain why that assumption about eigenfunctions following the manifold is actually kind of correct. Okay. What's the algorithm? So this is the full write-up. If you do not want to read this, I will just describe what you do. Take a point on your manifold, okay? And look at the vector to all of its neighbors, okay? Now this might be a noisy set of vectors, right? Because your neighbors might be moving in noisy direction. Equivalently, look at the first low frequency set of eigenfunctions. Take that point and look at all of its neighbors, right? The same neighbors, but look at the change in eigenfunction, okay? And what we're going to do is basically mean square error to approximate a Taylor series. We're going to say, all right, well, if I know the direction I've gone in my ambient space times this thing I'm trying to estimate, which is a gradient, that should more or less be the change in the function, right? This equation right here of CI in the middle is basically a first order Taylor series, okay? And now I just want to minimize that across my choices of how I pick these gradients. But this is a very high dimensional problem. I'm going to have a bunch of gradients at a bunch of points. This is not well posed. So how do we well pose it? We well pose it by pointing out that the gradients themselves are functions. And those functions are smooth, which means those functions can be represented as a sum of eigenfunctions. Okay? And so you can set up this mean squared error problem where you just have, you know, your local change in the coordinate system, your local change in the eigenfunctions, and then the gradients you're trying to learn, which are really just a function of combinations of eigenfunctions per gradient function. And it turns out this can just be solved. This is mean square error. You just solve. You use a pseudo inverse of x, and that gives you your C. And now that I have that, I now have at the point xk gradients, estimates of the low frequency eigenfunction. Okay, that's the idea. And now that's a high dimensional coordinate system. But it turns out, because our data was only varying along low dimensional manifolds, that thing is actually going to be low rank. And so we just compute an SVD, and that is our local PCA projection. Now, it's not PCA, but it's a local low-dimensional projection, linear projection matrix, okay? But derived from the eigenfunctions. And that is the algorithm, okay? I will show you in a minute why this is useful, but that's fundamentally the idea, okay? Now, I've made a very big assumption here, right? My assumption is that these eigenfunctions are robust to noise, that they only vary along the submanifold, the low frequency. How do we actually establish that?
Excuse me.
We
Yeah,
also
questions?
have a go for it, Hrishikesh.
Yeah, so isn't this U phi an infinite matrix? So the CI.
No, this is only of the low dimensional subset of eigenfunctions.
Oh, so you're taking a projection of the gradient.
That's right. That's right. I'm projecting the gradient onto my low frequency eigenfunctions. That's right. Okay. So yeah, M is some number. It's much larger than the intrinsic dimension, but it's much smaller than N. That's kind of the idea. Okay. Okay. This is the algorithm. Now, I want to motivate the fact that this is actually the case. So I'm going to show you, we have two in this paper that I'll show you I'll show you the paper reference in just a second. We have two kind of independent ways to talk about the fact that eigenfunctions actually do kind of follow this behavior. One is very differential geometry. One is entirely random matrix theory. They're complementary. Neither of them fully prove what I am claiming, but both of them imply a very, very similar condition. Okay. So there's a lot of technical stuff here. I just kind of want to describe the overarching idea of what we're saying. Say you're on a manifold that has a little bit of noise. So this T epsilon R is going to be, R is the reach of our manifold. T is going to be a tube around the manifold, and the radius of the tube is some epsilon times reach. If epsilon goes to 1, it's not a manifold anymore. You've violated the reach. It's just a completely different thing. But if it's some fraction of the reach, then you just have a little tube around your manifold. And in that setting, we can define two things. One, we can define the energy of the eigenfunction varying along the submanifold. And the other is we can define the energy of the eigenfunction varying normal to the submanifold. Okay? So the energy is going to tell us like how much is the eigenfunction varying in those directions. Okay? That's this E beta and E beta complement. And what we show is if we have an eigenfunction of the noisy manifold, the eigenvalue has to follow two things. The eigenvalue is going to be lower bounded by some properties involving curvature and reach and tubular size. But the key here is this last term. It's going to be lower bounded by something multiplying the noise, the variation in the normal direction. Okay, so what does that mean? That means if my eigenfunction really did vary in the normal direction, then by definition, the associated eigenvalue must have been large. Okay? And then similarly, we bound the opposite direction. You can upper bound the eigenvalue by similar constants times the variation in the manifold direction, plus something varying in the normal direction. So what does this say? This says if my eigenfunction mostly varies in the submanifold direction and doesn't vary in the tubular direction, in other words, this term is 0, then I have an upper bound. And I want to note that these two bounds look similar, except for the fact that that lower bound has an epsilon to the -2, and the upper bound doesn't have it. So what this is establishing is that there's a gap here. If your function doesn't vary in the normal direction and is low frequency in the submanifold direction, the eigenvalue won't be too big. And then there's a huge gap. And then if the eigenfunction does vary in the tubular direction, the eigenvalue must have been at least so big. So this is not fully right down like exactly the type of variation we're talking about, but it does imply that if we look at the low frequency set of eigenfunctions, they're mostly made up of functions that vary along the manifold direction and are pretty constant in the tubular direction. Okay. So this is one direction that we went that I think we really get something interesting here, which is that, there's this is pure differential geometry approach that really does tell us that the eigenfunctions agree with that assumption that I made about the low frequency set of eigenfunctions when you're dealing with tubular neighborhoods. All right, take that out, throw it away. We're going to come in from a completely different perspective.
Hi, Alex. So could you explain what is kappa perf? There's so many notations. So.
Oh yeah, no, sorry. So the kappa is actually it's the curvature. It's the curvature of your manifold.
Okay.
Yeah, sorry.
Thank you.
Oh, kappa perp. Oh shoot. I apologize. I have to remember. I forget. I want to say it has something to do. No, curvature in the codimension direction wouldn't make sense. I will answer that question after. I apologize. I'm blanking on what that constant is at the moment.
Thank you.
But I can promise you that in general, the real key here is these are constants that are handleable. The real key here is the epsilons and the energies. Yeah, sorry about that.
Thanks.
Okay. All right, so forget about differential geometry, come from a completely different perspective. What if I just had a point cloud? And the point cloud came from a nice structure. Okay. But then I don't see the point cloud. What I see is noise. Okay. I see my data plus some, and in this case, we're actually not going to have to deal with tubes. We're going to actually be able to have tails. So some Gaussian, some noise with variance proxy epsilons. This is mostly going to be like sub-Gaussian noise. Okay. So we're building a kernel not on the clean data, but on the noisy data. And then we build it with a Gaussian kernel with bandwidths. It turns out that if the noise is not too big, and again, this is not a perfect assumption. I want to move past this. But if the noise is not too big and is kind of, the variance is getting smaller as we get more points, it kind of winds up bounding the amount of variation that you can have of your noise. This is not my favorite assumption in the world, but it's something that, it's a starting point, right? That our noise variance is bounded by something involving 1/squared. Then we can actually say something really interesting. This Laplacian, the L bar, is the unknown Laplacian on the clean data. And the L is the Laplacian on the noisy data. Now, to be clear, both of these are actually normalized Laplacian, the random walk normalized Laplacian. I'm sorry, they're symmetric normalized Laplacians in this case. Then there's a concentration inequality. It turns out that these two Laplacians, as the number of points grows, is going to get smaller and smaller and smaller. Okay, so this is nice, and this is with high probability. The point of this is the following. If you had eigenfunctions of your real Laplacian, and you had eigenfunctions of your nice unknown Laplacian, if we assume that for the first few eigenvalues, there's a little bit of a spectral gap. This is hard to prove, but this is actually a common assumption that sort of empirically is true. Then it turns out that your eigenfunctions of your noisy Laplacian and your eigenfunctions of your true Laplacian are actually going to agree with each other quite nicely. So again, what this suggests is that if we really only focus on the low frequency eigenfunctions, they're going to agree with the object we actually cared about and not reflect the noise. Okay? So these are two motivations. There's a lot of fun build up to these if you want to delve into it. I didn't want to make these the center of my talk just because I want to focus more generally on the manifold learning. Okay? But I highly encourage you to go look at these. Dhruv and Sawyer, the two students that we worked with on these, just really knocked them out of the park as far as describing with. I think these results are of independent interest. Let me put it that way.
There's a question about what the omega means in the second corollary.
Omega is that the gap is at least n to the -1/2. I believe it's an opposite of big O notation.
Yep, that's what I thought. Thanks.
Yeah. And little o is the smaller than big O, so it actually does decay. Yes. So yeah, what this is saying is that there had to have been a little bit of an eigengap. It doesn't exist as n goes to infinity, but for low frequency eigenfunctions, this kind of is the case. Okay. Eigenvalues, sorry. Okay, so these are a couple of statements that kind of motivate my algorithm, but I want to motivate it also empirically. Okay, so remember, we estimate gradients, we take PCA of the gradients, and then that is our estimate of the local tangent space. So let's do that. You have this example I showed before. We have a ground truth and we have local PCA. And you see in local PCA, anywhere you hit a high noise region, you are not getting correct gradients. But look at the Lego algorithm with the exact same number of nearest neighbors. Okay, so remember, took the data, global Laplacian, take the eigenfunctions, use that to locally estimate PCA of the gradients. And it follows almost perfectly. High noise region, low noise region, doesn't matter. This is a good estimate. Okay. And we can do this in a lot of situations. You can look at the discrepancy between the true and estimated tangent vector angle, noisy Laplacian PC or local PCA. You see that it gets noisy exactly where you have high noise. Lego, you pretty much nail it at 0, except for a couple of weird extremal points. You can keep going. Very, very high curvature type manifolds, add noise to it. Look at local PCA, you get nonsense. Look at Lego, the exact same number of nearest neighbors, you get an incredibly strong estimate of the gradient directions. Okay. And you can keep going, right? I can look at, for example, the downstream way to do this. What if I wanted to do manifold learning, right? What if I want to piece together all these little pieces into one big manifold? I'll describe how to do that in a minute, but if you do local PCA, you're going to get a really bad embedding. This would be like if you did local tangent space alignment. But if you do Lego, boom, you nailed it, because you had good estimates of the local views. And also, I want to emphasize that this rank assumption that I'm talking about really does hold, right? If you look at local PCA and create like a scree plot across a lot of different instances, a lot of different points, you get these violin plots, right? So it's like sometimes the PCA, the first eigenvector makes up 70%, sometimes 50%, 25. The third, this is all, for this example, this is all two-dimensional data. So you should not have a contribution in the third direction. There's only two directions. The noise is the third direction. But with local PCA, you can't get rid of it. If you look at the PCA of these eigenvectors, gradients of eigenvectors, there's no third direction. You've lost the noise. It's gone. And so you really do have a locally two-dimensional hyperplane. Okay. And by the way, I'm showing this on clean manifolds. I'm going to show this on real data for a moment. So this is my favorite data set, courtesy of Roy Letterman and Ronan Thalmann back in the day at Yale. They had this beautiful thing where they took videos of a Yoda and a bulldog. It turns out there's a bunny off to the side. I'm not going to deal with that right now. And you're watching them spin independently. Okay? So because they're spinning independently at different frequencies, it turns out that if you took all those images and tried to piece them together, they would form a torus, like a 2D torus. Okay? Now I want to make the problem harder and just noise it. And so this is the data I'm going to work with, this noisy data. Okay? But I'm going to follow the whole process that I talked. So first off, you can just do a global PCA and then maybe visualize some of the PCA. You start to see a little bit of structure. So we're going to work in 10 dimensions. Like just do PCA down to 10 dimensions, and then we can do some manifold work. Okay. So if you do local PCA and then try to piece together all the local patches, it's going to be very hard to do. If you do Lego and try to piece together all the local patches, you're going to get an almost perfect embedding of a 2D torus. And it turns out, and I'll explain exactly what all of this means in the next set of slides, but basically it turns out you're getting this incredibly faithful set of low-dimensional views, local views, that's describing when the bulldog and the Yoda are pointing in the same direction. And I'm showing the clean images here, but this was done on that insanely noisy data. So this really is accomplishing something you can't accomplish with PCA. Okay. And again, you look at the eigenvalues. It really should be a 2D thing. We're really kind of getting a 2D thing. If you do this with local PCA, you're estimating that it's like 9-dimensional. Okay. So that's kind of the summary of Lego. That's the summary of the local views. Okay. You take eigenfunctions that have high gradients in the noise direction. They will always lie deeper in the spectrum. So we focus on the set of low frequency ones. You get this nice orthogonalization. And at the end of the day, it gives you a local hyperplane, which means if you have new points, there's a trivial out of sample extension. It means you can describe it. It's not intrinsic. It's an extrinsic dimension reduction, which is nice. So if you're interested in any of the details of this, this is our most recent paper, actually, robust tangent space estimation, Lego. I'd recommend taking a look. All of the proofs of all of the theorems I mentioned are in there. So that's the local view. So I'm going to stop on the local view. I'll see if anybody has any questions. My next part is about piecing these together. Okay, cool. So let's go to the global. All right, I am now going to assume I have a bunch of nice local views. For a small subset of points, I can tell you exactly a good extrinsic coordinate system or intrinsic coordinate system or coordinate system of those points. But now I need to figure out how to put them all together into something that makes sense. So that's the second question. Okay. So this really breaks up into two parts. The first is how do you align them? And the second is how do you show that this actually did a decent job? So it actually breaks up into two separate papers. So the first, what's the algorithm? The algorithm is basically, we build a bipartite graph. You have all of your points, endpoints. And you also have all of your views. And each point gets mapped to several views, right? Because your views overlap with each other. So we're going to define xki as basically the kth point in the ith view. Okay? And the way we align is anytime xk has a representation in view I and a representation in view j, they better be the same representation. They better lie on top of each other. Okay? And that's really how we're going to piece this together. And so it turns out you can frame this as a synchronization problem, right? You're trying to embed each view. you're allowed to apply some, currently it says question mark, but it'll basically be some orthonormal transformation of your view. Because like, you know, you get a view, it might be tilted, it might be inverted, like, you know, I don't know, there's parity, right? And you're allowed to shift it around a little bit. And then you have another view xj, you have another view j, and you're allowed to do the same thing to j. And it better be that when 2 points k are seen by both of those views, when 1 point k is seen by both those views, it better get embedded in the same point. Okay? And so we're trying to minimize this object, which is really hard. Okay? And that's the idea, right? xk, xki, xkj, we want to make sure that they kind of lie on top of each other after we rotate and shift them around for the set of points seen by both views. It turns out there's an equivalent way to do this, which is that you only define the rotations one time, and instead you have a proxy variable that is your global embedding space yk. That's like that's going to be my global coordinates when I'm all done. So you can show these two problems are equivalent to each other. Okay. So how do we choose the space of our things we're allowed to do to local views? Well, you could do affine, which is you're looking for local coordinates, yks, that are orthogonal to each other. This characterizes a lot of our eigenmap methods. But it turns out it doesn't give you the thing that you want. I want to look at rigid. I want to look at things that are allowed to act with some arbitrary orthogonal transformation to each rigid transformation of each local view. And it turns out both of these problems can be rewritten to be problems about the trace of a particular set of matrices. Okay, so you can solve the affine problem pretty nicely. There's a lot of work on this. This is what a lot of manifold learning techniques do, but it suffers, and I'll show you why in just a second. I'm going to focus on this rigid problem, which is harder, but will give you a better result. Okay, so affine isn't great. Why? Well, for example, when you do affine transformations of, say, a Swiss roll, you can lose aspect ratio, right? You wind up creating compressions because you're looking for orthogonal things, and that kind of distorts what the geometry was. You won't have that with rigid alignment. Similarly, in noisy data, when you do affine alignment, you can wind up leading to a lot of collapses, right? Multiple eigenfunctions varying in the same direction, and thus your embedding doesn't really look right. Or like they collapse on top of each other. That's not good. That's really bad for downstream analysis. If you have 2 points that are in the same place in the embedding, but fundamentally different places in the actual data. But with rigid alignment, that won't be a problem. Okay, so I really want to focus on rigid alignment. And in particular, this is the problem we're trying to solve. Minimum over all possible rotations across all of our views. I'm sorry, orthogonal transformations across all our views of this very particular problem, right? And C has a very particular form related to the Laplacian of that bipartite graph. There's a million ways you can solve this. Generalized Pursuits, Riemannian gradient descent, spectral relaxation, generalized power method. Everybody's got an approach. I want to focus on Riemannian gradient descent. I'll show you why in just a sec. Oh shoot! I thought that I thought the next slide was something else. That's fine. Riemannian gradient descent. It turns out it shows the fastest convergence, and we can still prove some stuff about it, right? And so the reason it's Riemannian gradient descent is you're doing gradient descent on S, where S lies on a manifold. So you gradient step, project back onto the manifold. Gradient step, project back onto the manifold. This is the right way to do it. This is the fastest way to do it. This is the most efficient way to do it. But we have to analyze it. And so what we have is a couple of results. Don't worry about what this capital L is. It's basically like a Kronecker product version of this Laplacian that's here. It's just this massive, massive matrix. But it turns out we can characterize times where you will get like necessary and sufficient conditions for saying that you will get a non-degenerate alignment. You'll get an alignment that like you're getting a unique minimum of that optimization scheme. And I should just note, by the way, you're getting a unique minimum up to a global rotation. You're never going to be able to do it up, up to the global rotation is always going to be there. So it turns out you need to take like this orthogonal transformation to the M and turn it quotient out by a global rotation. I won't go into the details of this, but well, there's a quick mention of it here, but it leads to a couple of really nice results that we can actually show. So the first is I start with some layout, okay, S0. if my S0 layout, my initial just lay down all my patches and take a guess of where they should be. If it is not too far from the global minimum, then we can prove Riemannian gradient descent converges linearly to the global. So if we've started in the well of the global minimum, we will converge linearly with Riemannian gradient descent. And we can characterize exactly what the radius is. It's in terms of a lot of constants that I don't feel like getting into right now, but you can characterize how big that well is going to be. Okay. And also you can characterize that, and this is the thing, this is what gets really fun about it. You can characterize two additional statements. First is, my local views are good, but they're not perfect. Turns out xki may be some true xki plus a tiny bit of noise. So I have noisy local views. Also, I need to initialize somewhere, and I need my initialization to be good. So it turns out under these settings, if you initialize with spectral initialization, which has a very nice closed form, easy way to get that initialization, that under noise puts you in the sufficient neighborhood of S. And we characterize it according to the amount of noise you can add. It has to be less than that delta. And if you are there, if your noise is not too big, such that the spectral embedding gets you somewhere close to the global correct embedding, Riemannian gradient descent converges linearly fast. So that's really the sort of central tenet of this, right? There's technical statements. This is not, technical assumptions, a lot of constants floating around. The key here is just the fact that as long as your noise keeps you inside that radius, you're going to be okay. All right? Yeah, and here's what I wanted to show before. I mentioned there are all these different approaches to doing this. Blue is Riemannian gradient descent, global pursuits, method pursuits, spectral initialization, all these things. I'm showing here a plot. X is the number of wall clock seconds for running something on, I want to say it was like 10,000 points. And then Y is the alignment error. Semi-definite programming. You can prove things. It is insanely slow. And it doesn't work with a lot of points. In fact, we can't really even do this. I think we did a subsampling of the number of points here. Global pursuits. It goes fast, but it doesn't get you great alignment. Spectral initialization. Great, but doesn't get you to the minimum. Pursuits actually gets worse over time. Riemannian gradient descent. Boom, done. Initialize with spectral, run it, linear convergence to your global minimum. And if we look at the final alignment you're going to get, this is my initial alignment. All the colored dots here you're seeing are basically like where patches have been ripped apart. Like I'm just laying them down in this kind of weird way that's not great, right? And then you run this alignment to find the global minimum. This is your Riemannian gradient descent. It looks correct. It looks by far the most correct, okay, of a straight line with high aspect ratio. Yeah, and it turns out, okay, I'm actually, for the sake of time, I'm going to go ahead and skip the next thing. It turns out there's like 25 different notions of alignment, and we have a bunch of ways to sort of relate each one to the other. So everybody's got their favorite notion of alignment. Infinitesimal, locally rigid, globally rigid, affine alignment. It turns out you can really kind of put conditions for all of these things to be equivalent to each other. So I'm not going to delve into that now, but what I do want to delve into is a follow-up. Okay, so now what do we have? We have a method for finding nice local views. We have a method for aligning our local views. Once we start somewhere. I've not specified where, but we start somewhere, and then we have a method for aligning them to get really, really nice, really, really fast. So where do we start? And this gets into a really fun additional topic called tear and repulsion alignment. So what is a problem with a lot of the ways we think about manifold learning? A lot of manifold learning algorithms cannot embed into the intrinsic dimension of your data. And in particular, like if you have a circle and you're trying to find a way to globally embed that, it turns out you're never going to be able to do it because there's no homeomorphism of a closed manifold into its intrinsic dimension. It just doesn't exist. So what we do is we say, all right, I don't care. I'm going to do what a mathematician does. If I show you a torus, how do you imagine it? You imagine it as a straight line with gluing instructions that say, once you've gotten to one end, jump to the other end. Right? That's how we picture torus. And that is embedding into the intrinsic dimension, just with this additional little component of what we tore apart. So I want to do that with manifold learning algorithms. I want to embed into an intrinsic dimension, but in a way that I can, maybe cut a little. Okay. So how's this going to work? The algorithm, the flow, is basically going to be, all right, we have an input dimension, an input shape, maybe a sphere or something. Great. I want to just cut it somewhere. Turns out I know how all the patches relate to all the other patches. So I know it is a sphere. But I'm just gonna break some of those in that bijective graph of points and views. I'm just gonna cut them. And it turns out you can kind of cut them anywhere. It's not really a big deal. And I'm just gonna create what I'll call an over-torn embedding. The way we actually do it is a tree-based alignment. You sort of start with like a very central view and then kind of in a tree-like fashion lay down things. And then if you ever run into a contradiction, you just say like, nope, tearing that. And so you just kind of put all of your local views down on the page. And it will look something like an over-torn embedding. Okay. And then using Riemannian gradient descent, we stitch it back together. And that winds up getting us our nice embedding with this notion of how, any point over here kind of should be attached to a point here. And any point in the blue over here should be attached to the point in blue over here. Okay. And it really does create a embedding, a low distortion embedding of our sphere. Okay. So given that, I want to also just mention real quick that like, all right, we can tear, we can embed, we can rotate. What is the distortion we're creating? Okay, so you can measure distortion. You can measure manifold distortion. It's basically the condition number of your embedding, right? What is the maximum stretching you did? What is the maximum shrinking that you did between any 2 points? That ratio is your distortion. So distortion is always going to be greater than or equal to 1. It's a condition number of the function that takes you from the output data to the input data. I'm sorry, from the high dimensional data to the low dimensional. What is its distortion? Okay. And there's a million different notions of distortion. There's what's called strong distortion, which is you look at the path between any 2 points in the high dimensional space. You look at the shortest path between any 2 points in the low dimensional space, take a ratio. Then you take it of the biggest ratio, and then you do low distortion, low dimension divided by high dimension, take a ratio, and that gives you this global distortion, right? So that's strong global distortion. There's another version called weak global distortion, which is you take the path in high dimension, and then you take that same path in low dimension, and you measure its length. And then you take the path in high dimension, the shortest path, and you take the same path in low dimension, and you look at those ratios. So the one is global, one is global strong, one is global weak. Turns out you can characterize some things like if you have low weak distortion and high strong distortion, that means your embedding is collapsed. If you have low strong global distortion, that means you preserve the geometry. Okay. And there's all these notions that you can have floating around, but at the end of the day, what can we say? So at the end of the day, what we can say is a really nice little theorem that says we can bound the weak distortion. Okay. How do we bound the weak distortion? It is bounded by the amount of local distortion we had. That came from local tangent, the Lego algorithm. If you have a nice local view, kappa is small. Some epsilons that have to do with the curvature of the manifold, things we can't get away from. And these two constants, which are basically related to our alignment error. So what this is saying, this is the thing we're optimizing. We're optimizing FFS. So what this bound says is the weak global distortion is bounded by how bad our local views are and how bad our alignment error is. And as our alignment error gets better, the weak global distortion goes down. So that means that our Riemannian gradient descent is making a better embedding. Okay? And in particular, like if you have perfect local views and you have perfect alignment error, then you can show that the global distortion of this algorithm is just a function of the curvature of your manifold. You can kind of, you're taking a curved manifold, flattening it into a flat space. You're always going to cause a little bit of error. Turns out that's the only error you're causing in that case. Okay, that's for weak distortion. Turns out for strong distortion, you have to make an additional assumption. Basically says that you've had a little bit of repulsion. 2 points that were close in the embedding space have to be close in the data space and vice versa. If you make this assumption, it turns out this same bound applies to global distortion. Okay, and so what this motivates is one last little statement, which is we now have all of these tools, which is like, how do we initially lay down our points? How do we refine? How do we get nice local views? The one last thing we have to add is that you want to make sure that if 2 points were far apart in the data space, they're far apart in your embedding space. And you can do that very trivially in this optimization scheme by adding a repulsion. Just take points that are far apart from each other and make sure they embed far apart in your embedding space. You repul. So now we have an attraction term here, and we have a repulsion term on that second term. And you can actually build up this entire thing and get that this problem is basically just a function of the Laplacian of signed graphs. And then you can apply all the stuff I talked about Riemannian gradient descent there. It still works. So now that kind of finally pulls together the whole story, right? You can find good local views. You know the right way to lay down your points initially. You know the right places to tear so that you don't have collapse. You know how to refine in such a way that you make sure far points stay apart and close points stay together. And you can bound the distortion based off of those other quantities, right? So I'm going to show some examples in a minute, but just that's kind of the summary of the algorithm, right? That's like the whole kind of pipeline, right? And I know this kind of, I'm running through a lot of different things, but unfortunately, this will wind up being like as a culmination of like 5 different, partial approaches to these problems. Each one of these winds up being sort of a paper where you got to prove some fun stuff. But at the end of the day, I think it really does create the right algorithm for doing low-dimensional embedding. Okay. So I'm just going to I'll just do a quick slide and then I'll be done. But downstream applications, right? Does this really work? So I'm going to focus on neuronal activity. And I want to pick this example because I love this example. You study a monkey brain. And in the monkey brain, there's like 74 neurons. So you have a 74-dimensional input. And the monkey is doing 2 things. Cranking a wheel, and he's cranking it at different speeds. Okay, sometimes slow, sometimes fast. There are motor cortex neurons in the brain that are measuring exactly those 2 things. They are telling the brain how fast it's moving in the relative orientation of the arm. Can you see that? That's the question. And so it turns out, if you try to use TS&E, you are completely out of luck. If you try to use UMAP, you are completely out of luck. If you try to use isomap, you start to get something, but there's no way to embed it into a low-dimensional space. And if you use our Riemannian aligned tangent space algorithm, this isn't even using the Lego stuff. This is prior. This is just local PCA. So the Lego is now the follow-up. But if you use this Riemannian aligned tangent space analysis, this is your embedding. So what are these two colors, right? The first color is the points colored by how fast the monkey was moving at that point. And you see that we get a clear direction of slower to faster movement. The motor cortex neurons are ramping up as it moves faster. And similarly, you see a left to right behavior orthogonal to that. That is the angle that the monkey's hand was at. And it is orthogonal to the speed that they were moving. And this embeds into a toroidal structure, because if you get to here, we just kind of artificially colored these points. That says jump back over to the other side. So we really are getting that this is a torus. It's a ring, right? And you can do this by like looking at decoding angle. So like really trying to regress against what angle their hand was at, because we know that information from side information. We're not using it in the embedding, but it does exist. And it turns out that if you look at the delta here, you're getting an almost perfect alignment between what the low dimensional coordinate system we create in rats and the actual angle that that monkey's hand was at. And it is, this is, this works. You're getting the lowest mean square error, right? We can do this with some other things that have to do with like, there's some neurons in the brain that can help a mouse understand where they are in 2D space. And again, we can get very, very clear embeddings that actually work really well. And it turns out from this, we can do things like persistence diagrams to show that it really is a, two-dimensional torus or something like this. But yeah, that's kind of the summary, right? So I'm going to kind of stop here and just, I'm saying this to say that like, I think this puts together a nice pipeline of how to think about manifold learning. If you know you have good local views and you know how to start laying them down and you know how to align them, you've got a good way to create a low dimensional coordinate system. And once you have that, it's guaranteed to be good and you can use it for your downstream applications. So we're going in a bunch of directions with this, looking at different regions and how to parameterize, how to understand how stochastic differential equations behave in the low dimensional space versus high dimensional space, multimodal problems, task-based problems where you're doing feature extraction. One of my colleagues here, Vishal Patil, has a lot of stuff where you have like worms that are tangled all about. You want to get a parameterization of each worm. So you want to kind of take these highly complicated structures and break them up and really lay it out like that was one, that was another, that was another. So these are kind of the directions that we're going right now, but I want to emphasize, I think this is a really cool algorithm. Everything's available on GitHub if you want to take a look, and all the papers are out. And also in 2 years, if you're looking for people to hire as a faculty member, Dhruv is the best mathematician I've ever met in my life. No, he's amazing. And I would highly recommend, checking out all of the work that I'm sure he's going to do over the next few years at Princeton. So anyways, that's that. Yeah, thanks.
Thank you.